Lesson 10.3, Power Series and Interval of Convergence. We have studied infinite series and learned about Taylor polynomial approximations. In this lesson and the next, we will explore how many functions, such as e to the x, cosine x, and sine x, can be rewritten as polynomials with an infinite number of terms. Taylor and Maclaurin series are actually specific kinds of power series. A power series has a variable in it. If x is a variable, then an infinite series of the form summation from n equals 0 to infinity a sub n times x to the n is equivalent to a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus dot 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 a sub n times x to the n plus dot 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 dot, right? Goes on into infinity. This is called a power series. While an infinite series of the form summation from n equals 0 to infinity a sub n times x minus c to the n is equivalent to a sub 0 plus a sub 1 times x minus c plus a sub 1 or a sub 2 times x minus c squared plus dot 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 plus a sub n times x minus c to the n plus dot 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 is called a power series centered at c, where c is a constant. Taylor polynomials centered about x equals c have the form p sub n of x equals f of c plus f prime of c divided by 1 factorial times the quantity x minus c plus f double prime of c divided by 2 factorial times the quantity x minus c squared plus f triple prime of c divided by 3 factorial times the quantity x minus c to the third plus, and then of course that nth one is the nth derivative divided by n factorial times the quantity x minus c to the n. So we're going to start off with example number 1, just considering a function, and if we were going to write a Taylor polynomial for that function centered at this point, could we do it or not? It says some function shown below will not generate a Taylor polynomial at x equals c because the function or one of its derivatives do not exist there. Determine which functions present problems and explain why. So we are just looking at what our domain would be and thinking about, could we center something at that point? So let's first look at our domain for y equals the square root of x minus 1. And I think everyone knows that this is going to be bracket. Oh boy, my pen likes to mess with me. Come on, bracket 1 from 1 to infinity. And so 2 is inside that. So we should have no problem at all centering a Taylor polynomial at 2 for that function, okay? For the next one, our domain would be, we cannot include 1. We want 1, but non-inclusive to infinity for that domain. So could we center it at 1? No, it's not. 1 is not a part of our domain. So I say the domain is from 1 to infinity, which does not include 1. So f prime of 1 does not exist. So no, we cannot have a Taylor polynomial centered at 1 for that function. The next one, y equals the cotangent of x. Everyone remembers that cotangent x is cosine x over sine x. And so we know that we do not have values for this domain where sine of x is 0. And so sine of x is 0 at x equals 0. So this answer is going to be no. I just think I'm too close to the edge there. If I move that. Maybe I'll have a better time. No, there is a vertical asymptote. At x equals 0. So y equals cotangent of x is undefined at x equals 0, or however you want to write it. You're getting the gist of it. All right, D, y equals the square root of x plus 1 would have a domain from -1 to infinity. -1 is in the domain, but is the function differentiable at -1? If we took the derivative, you would see that it is not differentiable at -1. Okay, it is not differentiable at that endpoint. If I took the derivative of that, it would be 1/2 times x plus 1 to the -1/2. So you can see that that derivative, 1 over 2 times the square root of x plus 1, is undefined at x equals -1. So even though -1 is a part of its domain, it is not differentiable there, which is another thing that you need to have to write a Taylor polynomial. So y is not differentiable at x equals -1. So the answer is no. Can't do a Taylor polynomial there at centered. We can do a Taylor polynomial on all these functions, just not centered at that value, right? Okay, so letter E, y equals the square root of x minus 1. So our domain is going to be 1 to infinity. 0 is not in the domain. So no. Y equals 1 over x minus 3. Our domain is -infinity to 3 union 3 to infinity. 4 is in the domain. It would be differentiable at 4. So this one's okay. I just can't get my pen to write. I think it's because I lay my hand on another part of the screen when I do that. I'm trying not to, but it's really hard not to. Okay. So there are 2 issues you want to consider. First, we've seen that except for geometric or telescoping series, we can't sum most series with an infinite number of terms. And also, not all Taylor series will converge for all values of x. But we will show how infinite Taylor series, which are Taylor polynomials with an infinite number of terms, will be exactly equal to their parent functions for x values that converge. So, when we're writing these Taylor polynomials, some of them are good for only one term, or, for one value. Some of them are good for an interval of values, and then they go bad. And some of them are good for the entire domain of the function. Okay, so from -infinity to positive infinity. For sine and cosine, when we write a Taylor polynomial for sine and cosine and we take it infinitely many terms, it is exactly the same as sine and cosine. So those are 2 examples where that is true. You can see the 4th degree term in this example down here in this little sketch. Look, that's a Taylor polynomial to the 4th degree, and look how it is almost exactly the same. For certain values, you can see that it's like right the exact same function. They would have such close y values, and I mean, as you made that bigger, you can see that for certain values, that is an excellent approximation. But of course, you know, that's where we get into our interval of convergence, because at a certain point, they start to get, you know, too different than one another to use it as a comparison, you know. Because what we're trying to do is we're trying to take a polynomial function and use that to talk about a certain part of a function that's difficult to talk about without a calculator. Okay, so if I wanted to put, you know, x values in ln of 0.4, that's not very easy, where I could put 0.4 up here and have an okay time. I could figure out my y value. I could figure out, you know, things about that function. All right, so example number 2. Given f of x equals ln x, construct a Taylor polynomial of degree 4 centered at x equals 1. So let's go ahead and practice that. We have our f of x. I'm trying not to put my hand on the iPad. And then since they want to center it at 1, we're going to calculate f of 1, which is 0. And then we take our first derivative, 1 over x. Whew, this is hard to do. Maybe just like another color. Do you guys have these memorized yet? Sometimes I feel like we take the derivative of 1 over x so many times that we start memorizing, and then we kind of see the pattern that it goes from negative, positive, and it keeps increasing, right? So we have that fourth derivative is negative 1 over x to the fourth. And then we've got our f of 1, we said was 0. We've got our f prime of 1 is 1. Our f, oops, I accidentally put x. You knew I meant 1. Our f double prime of 1 is negative 1. Our f triple prime at 1 is 1. And our fourth derivative at 1 is negative 1. Okay? So now we're ready to write our Taylor polynomial of degree 4 centered at x equals 1. So remember, if it's centered at x equals 1, our first term is just going to be f of 1. That's 0. Then it's going to be the derivative at 1 divided by 1 factorial times x minus 1. So this is just going to be x minus 1. And then plus our derivative at 2, which is going to be a negative 1 over 2 factorial times x minus 1 to the second. And it's going to be a positive 1 over 3 factorial times x minus 1 to the third. And a negative 1 over 4 factorial times x minus 1 to the fourth. So this is that fourth degree Taylor polynomial centered at x equals 1 for ln x. And then they want us to use our calculator to compare the original function to your approximation, and what do you notice? And, excuse me, so if you put that in your calculator along with ln x, and there's a picture right here, you would notice that the Taylor polynomial of degree 4 is only good for a certain number of x values, for certain values of x, is only good for certain values of x. And then it starts to fall off. And you really wouldn't want to use that anymore for an approximation. And I hope you notice that those values are, since this polynomial is centered at x equals 1, they are, like a radius away from 1, right? They're a radius away from 1, and I'm wondering what that is. So write out the general term for the series and then put it in sigma notation. So we can kind of see that if we were talking about the nth one, we'd still have your x minus 1 minus, this would be x minus 2 over 2 plus x minus 3, x minus 2 squared, sorry, over 3. Ooh, you know what? I forgot my 2 up here. I'm sorry. I forgot my 2 here. I bet you guys wanted to say Miss Lauschke, like you do in class, and I forgot my 6 up here. I'm so sorry. So that one is -6. So that one was a 6, and that one was a 2. Sorry about that. So when these simplify, there is just a 3 here, okay? And so this would be minus, and then when these simplify, I end up with x minus 1 to the 4th over 4, okay? So plus dot, dot, dot. Now we want to try and write our summation. So this is equivalent to from n equals 1 to infinity. Okay, I know that I go from positive to negative, positive to negative. I have to decide, do I need an n or do I need an n plus 1? Is my first one negative, because I'm starting at 1 for n. Is my first one negative? No. So I think I should use an n plus 1. So then my first one will be positive. Okay? You could have also said you're going to use n minus 1, because that would also give you the first one to be positive. So, but I just used n plus 1. And so this one is going to be x minus 1. And so it looks like we could say it x minus 1 to the first, x minus 1 to the second. So this is just going to be n. And then look, when you simplify these, taking the derivative and the factorial, this is just going to give you n at the bottom every time. And if I would have done my derivatives correctly, I was trying to go fast, and I was not showing my work, and I skipped my little coefficients up there. All right, so there's your summation. And then they want us to substitute x equals 2 and apply our convergence test. So we're going to take our summation, n equals 1 to summation n equals 1 to infinity, -1 to the n plus 1 times x minus 1 to the n over n, and for x equals 2, summation n equals 1 to infinity, -1 to the n plus 1. When I put 2 in here, I just get 1, so I really don't even need it, right? When I put a 2 in there, that's what my summation is. And we're going to apply our convergence test. So by the alternating series test, number 1, our a sub n is 1 over n. And our a sub n plus 1 is less than a sub n. Number 2, as n goes to infinity, a sub n is less than, or no, it's greater than 0. What am I saying? Less than 0. Jeez. It's greater than 0. And then number 3, the limit as n goes to infinity of a sub n is 0. So those were all the things that we needed for convergence with the alternating series test. So therefore, the series converges. And I can't remember, I don't know why they're talking about a little bit of, they just put a little thing about pi in there. I don't know why. Anyway, when does a power series converge or diverge? Okay, that is what we want to think about. What test do we use for determining convergence? So in general, the ratio test, sometimes the root test should be used to determine the radius of convergence. And so for a power series, because we were looking at this and we know that it converges, but not everywhere. And we know that we have converging alternating series, but diverging regular. So it only converges conditionally, okay? So that you should be thinking of that in the back of your mind, that this is only conditional convergence. So we have a power series in X can be viewed as a function of X, and where the domain of F is the set of all X for which the power series converges. Our main concern in this lesson will be to find the domain of a power series. It should be evident that every power series converges at its center, which means C always lies in the domain of F. The domain of a power series will take on 3 basic forms: a single point, an interval centered at C, or the entire number line. So for a power series centered at C, there are 3 possibilities. The series converges only at C, so only at that one point. There exists a real number R greater than 0 such that the series converges absolutely for the absolute value of X minus C is less than R, and diverges for the absolute value of X minus C is greater than R. Or number 3, the series converges absolutely for all X. So the number R is the radius of convergence of the power series. So if the series converges only at C, the radius of convergence is 0. If the series converges for all X, the radius of convergence is R equals infinity. The set of all values of X for which the power series converges is the interval of convergence of the power series. So in summary, the ratio test is used to find the radius and interval of convergence. The ratio test says that a series will converge if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. So we will find the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, and then determine the values of x for which the limit is less than 1. Every time you are asked to find the interval of convergence, you must check to see if the endpoints are included in the interval. Okay, so sometimes they're included and sometimes they are not. So please remember that. So that was a lot. I mean, you know, golly. This was super, 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 super important. You know, this was super, 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 super important. So all of this stuff you need to highlight and make sure that you are understanding. That was just a lot to say. So, find the radius of convergence and the interval of convergence. Be sure to check the endpoints. Okay, so we are going to work some problems here. Part A, summation n equals 1 to infinity of x minus 2 quantity to the n power over n. So the first thing we're going to do is we're going to use the ratio test to find the convergence. Oops. Sorry. So number 1 is ratio test. Limit as n goes to infinity, absolute value, x minus 2 to the n plus 1 divided by n plus 1, and then we're dividing by a sub n, which means we'll multiply by the reciprocal. And we're just going to see where this takes us. So I know that this is going to be x minus 2 to the n times x minus 2. And I know that these two will cancel. And this leaves us with x minus 2 times n over n plus 1. Now remember, if this part doesn't have an n in it, you could just pull it out to the front. You're really looking at what n over n plus 1 is doing, and it's going to 1. So this just leaves you with the absolute value of x minus 2. So we know that if this is less than 1, it's going to converge, right? So I'm just going to go ahead and I just want you to be thinking of that, because really we just took this ratio test and we only did the one side of it. And so we're going to say, now part 2, we're going to say that it converges when what we got it to equal is less than 1. Well, that means that this x minus 2 is between negative 1 and 1. Right? That's what that means. And so now we add 2, add 2, add 2. And now here's our, we can tell what our radius is right now. So our radius, because this is a total distance between 1 and 3, it's a total distance of 2, our radius has to be 1. So our radius of convergence is 1. Because it's 1 away on either side, right? So if it's a total distance of 3 minus 1, which is 2, then that means that it's 1 away from the center on both sides. So that's your radius. So now the third thing we're going to do is check our endpoints. Okay, and our endpoints are x equals 1 and x equals 3. So for x equals 1, we've got summation n equals 1 to infinity. And if I put 1 in, I'm going to have negative 1 to the n over n. This is the alternating harmonic series, hopefully you see this, that is conditionally convergent, right? So, and that's fine. We just need to know whether it converges. Because if it converges, then we need to include 1 in our interval of convergence, because this right here, when we get done, is going to be our interval of convergence. We just have to see, does 1, do I need to put an equal to sign on 1? Do I need to put an equal to sign on 3 before we actually say, hey, this is it, it's done? That's why I did not do anything with it yet, but we are going to decide. So if I put a 3 in, I get summation n equals 1 to infinity. This is going to give me 1 to the n over 1 over n. So this is just 1 over n, because 1 to any power is 1. And we know this is divergent. Divergent harmonic series, right? So we know that x cannot be 3. So this is your interval of convergence and your radius of convergence, okay? And that's how we do it. So now, part B. First thing we're going to do, ratio test. So we've got limit as n goes to infinity of the absolute value of n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. This one wasn't a fraction, so we were able to do a sub n plus 1 over a sub n. And now we just want to start simplifying. So this is, remember we've got our n plus 1 times n factorial, x to the n times x, n factorial, x to the n. And then our n factorials cancel, our x to the n's cancel. And that leaves us with x times n plus 1 there. And again, since your x doesn't have an n in it, you could bring that out front. So we're really just looking at what happens when n plus 1 goes as n goes to infinity. So you're going to get infinity. The only way that you wouldn't is if x were 0. So that means that 0 is the only thing that's going to give you convergence. So the radius of convergence is r equals 0 because there's only one thing. And the series converges only at x equals 0. So there is no interval of convergence. Okay, letter C. First thing we do, ratio test. Limit as n goes to infinity of the absolute value -1 to the n plus 1, x to the 2 times n plus 1 plus 1 over 2 times n plus 1 plus 1 factorial, and then times the reciprocal. Okay, so this one's going to be a little bit of work to simplify. We've got -1 to the n. We've got -1 to the 1. Now, this is going to give us 2n plus 3, right? This is going to be x to the 2n plus 3. We want to try and cancel x to the 2n plus 1. So let's do side work over here. So x to the 2n plus 3, we would like it to cancel with x to the 2n plus 1. So could we change this to x to the 2n plus 1 times x squared? Would we still have x to the 2n plus 3? I think we would. I think if we break it up like that, we're going to be able to cancel something. So that's what we want to do. So we've got our x to the 2n plus 1 times x squared over, now this is going to be 2n plus 3. Now we want to cancel it. Here's some more side work. we're going to have 2n plus 3 factorial. Well, that's going to be equivalent to 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. We're reducing it by 1 every single time. I'm going to add the factorial at the end. You can add it at the end at any point, but that's the one I want to cancel. So this is going to be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Oops. Okay, so now what can I cancel? I can cancel my negative 1 to the n. I can cancel my x to the 2n plus 1, and I can cancel my 2n plus 1 factorial. That's going to leave me with limit as n goes to infinity, absolute value. I've got negative 1 x squared over 2n plus 3 times 2n plus 2. So remember how I said you can take the anything that does not have an n in it to the outside. I'm just going to take that to the outside like that. Oops, that was supposed to be a... So now, if I put infinity into the denominator here, I'm going to get 0. And 0 times x squared is 0. So this whole thing is going to give me 0, no matter what x squared is. Okay, so no matter what x squared is, you're going to get 0. Is 0 less than 1? Yes. So for convergence, you need this to be less than 1. Well, it's always less than 1. It doesn't matter what x is. So what we're going to say is that this, no matter what x is, less than 1. So the radius of convergence is infinity. The interval of convergence is negative infinity to positive infinity. Okay? So there's one that is good for all values of x. Okay, let's look at D. Summation n equals 0 to infinity. We're going to first use our ratio test. And we're going to say the limit as n goes to infinity, absolute value, this is going to be negative 3 to the n plus 1 times x to the n plus 1 over the square root of n plus 1, and we're going to multiply by our reciprocal. And now we need to simplify. So we've got our negative 3 to the n times negative 3. We've got our x to the n times x to the 1 over, this is just going to be the square root of n plus 2. You can't really do anything with that, darn it. It'd be nice if we could, but we can't. And now we figure out, okay, what's going to cancel? We've got our negative 3 to the n canceling. We've got our x to the n canceling. And this is going to give us limit as n goes to infinity. Absolute value negative 3x times the square root of n plus 1 over the square root of n plus 2. And if you want to bring that, absolute value of negative 3x out, and got your square root of n plus 1 over your square root of n plus 2. What does this limit equal? Well, the strong term is square root of n. You could have written this also as right? So this becomes 1, and the square root of 1 is 1. So this whole thing, this whole limit becomes 1, right? So this becomes absolute value of negative 3x. This is what we need to be converges when the absolute value of negative 3x is less than 1. So now we're going to say, well, that means that negative 3x is between negative 1 and 1. And we divide by negative 3, divide by negative 3, divide by negative 3. And that gives us 1/3 is greater than, x is greater than negative 1/3. So let's go ahead and move that normal so that the smaller one's on the left and the bigger one's on the right. And this is your possible interval of convergence, right? Our radius is 1/3. Radius of convergence is 1/3. That you can see once you've written that, because it's going to go from 0 to 1/3, 0 to negative 1/3. So the radius is 1/3. Now we have to check our endpoints. So number 3. That's why I have not x equals negative 1/3 and x equals positive 1/3. That's why I have not circled this interval of convergence yet. But this is going to be our interval of convergence. I just have to know, do I need to put an equal to sign on either one of those? So I go and I say summation. This one's n equals 0 to infinity. This is going to be, and which one are we doing first? Let's do x equals negative 1/3 first, sorry. This one is going to be negative 3 to the n times negative 1/3 to the n over the square root of n plus 1. Okay. So do you see what's going to happen here? If you put both of these powers to the n together, you'd get 1 to the n. So that's just 1. So this simplifies to summation n equals 0 to infinity of 1 over the square root of n plus 1. Right? And, technically for that one, we would compare it to, we'd use a comparison test, 1 over summation, 1 over the square root of n, which diverges So our summation 1 over the square root of n plus 1 also diverges by limit comparison test. So we don't want to put an equal to sign on negative 1/3. So now we need to look at positive 1/3. Summation n equals 0 to infinity. We've got our negative 3 to the n. We've got our positive 1/3 to the n over the square root of n plus 1. So now this one simplifies. When I multiply negative 3 times 1/3, this one simplifies to negative 1 to the n over the square root of n plus 1. So this one's going to be an alternating series test, and it actually converges by the alternating series test. Because when you're, remember what diverges means, that these, when you add them up, they just keep getting bigger and bigger and bigger. But when you're plus minus, it actually converges. So that's the one where you have to be really careful, because some of these converge and some of them diverge. When you are just focusing on, you know, your 1 over the square root of n plus 1, and, you know, does the limit go to 0, right? When you take the negative 1 to the n off, does that limit go to 0? And is it, you know, getting smaller every time? And it is. Then you've got, you know, by that alternating series test, that gives you convergence. So we need to put an equal to sign on that guy. And now we have our interval of convergence. Okay, and our radius. All right, so a brief summary. Many functions can be written as power series. In fact, there are some in your book that we use, like this one right here, 1 over 1 minus x is equivalent to this summation. And sometimes we use that. Oh, and by the way, it's only valid from negative 1 to 1, but sometimes that's enough, you know, so, but sometimes we use that to find other power series. So a function written as a power series with center at x equals c is called the Taylor series with center at x equals c. By increasing the degree of the Taylor polynomial of a function, the approximation becomes more accurate. So, you know, that one that we looked at the picture of at the beginning of this lesson, if we would have increased it to 6 or 8, it would have widened our interval of convergence. So sometimes the Taylor series of a function converges only for certain values of x, so it is necessary to find the radius or interval of radius and or interval of convergence. There are some functions that are not equal to the sum of their series, but we are not responsible for these in our course or on the AP exam. So some functions are not equal to the sum of their Taylor series, okay? But we're not going to worry about those. We're only giving you the ones where they are. So now, I think you're ready to go. I did give you some Math Excel problems, and I think maybe I labeled the lesson numbers incorrectly. So what I would do is I would try to watch these videos, and I'm going to send you guys a note. I think you need to watch these videos and then go in and try and do that Math Excel. The Math Excel is coming from our textbook, and it doesn't flow. They teach things in a different order using